Alright guys, so in our last lesson we talked about free body diagrams, which is where we were modeling different forces. And that helps us lead us into the principles of statics and how we're going to utilize those diagrams to model different situations and design, particularly when we start to talk about designing for our bridges. So to start off, we have to consider Newton's laws of motion, and you may have seen these before. And they're all valuable for what we're going to talk about, but some of them we really need to keep in mind as we start to think about modeling some of these forces. So Newton's first law of motion, sometimes also called the law of inertia, is that an object at rest stays at rest, or an object in motion stays in motion unless acted upon by another force. And this is particularly relevant in a lot of physics applications, and it won't be particularly helpful in some of our statics problems, but it's useful to know. Newton's second law of motion has to do with how mass and acceleration are related to each other in terms of how an object moves. And so basically what it boils down to is force is equal to mass times acceleration. This is why, if you remember when we were doing our simple machines, if we measured in newtons, we had to multiply times 9.81 and our kilograms to get that force in newtons, because mass, or kilograms, doesn't take into account gravity, that 9.81, to get our force. Remember that for pounds, that already had our system of force in it. So this will be relevant if we're given something in kilograms and we want to make sure we're modeling that as a force. The third law is going to be the one that's of most importance for us, especially as we start to model some of our situations in free body diagrams. And you may have started to see this with some of the ones that we did last class, is that for every action, there's an equal and opposite reaction. So if you consider your free body diagrams, when you think about that normal force of the table supporting the book, it has that equal reaction, that equal force pushing up on the book as the book has pushing down on the table. So all of statics is based on this idea of static equilibrium. So static equilibrium is achieved when there's no net external force acting upon an object. So that means that object is completely at rest, or it's moving at a constant velocity. In order for us to be moving, accelerating, then we need to have a force acting upon it. So that ties back to that second law of motion. We need to consider also translational equilibrium. So that's when there's no unbalanced forces acting within or on the body. And so we see this sum symbol again, and we have sum of forces in the x direction has to be equal to 0, and sum of forces in the y direction has to be equal to 0. So they're balanced in both the x and y direction. And we use that sum symbol when we were doing the centroid, and we're going to get really used to using that a lot as we start to do some of our truss forces. The other thing that we look at is rotational equilibrium. Is the sum of all the rotations equal to 0? And we looked at moment very briefly in the last unit, and if you remember, moment is that distance times the force. And we can think about that example of the balanced lever or the seesaw, and where do we need to sit and where do we need to place that weight so that we have balance in our system. And we call this rotational equilibrium when we have that balance within our system. And again, that doesn't mean that it's not moving, but maybe it's moving at a constant rate. So that rotation is constant around some center or pivot point. For a moment, we need to consider whether we're positive or negative, and this will be really important as we start to look at our calculations. And there's no real trick to helping to remember this, but we need to know that counterclockwise is positive and clockwise is negative. So when we're characterizing which direction is that rotation when we're calculating moment, we want that counterclockwise to be positive, clockwise to be negative. If you think about kind of like our positive x-axis, if we're going counterclockwise from this positive x-axis, we start in the first quadrant if we're thinking about a coordinate plane. So that might be one way to help remember that counterclockwise is positive. So remember, moment is force times distance. So it's the force that is acting on the object So in this example, we have this red arrow here. That's our force, and it's the perpendicular distance from where that force is to where our rotation point is. So we don't want to use this distance, maybe the distance of our wrench, or if we had some more complex wrench, maybe we had something that looked like this, and this is where our force is acting, we're rotating about this point, we're still using this distance here. We don't want to consider this distance. That's a no. So we are going to start looking at vectors, and one of the ones that we use most commonly for our statics principles is force. Remember that force is a vector quantity, meaning it has magnitude and direction associated with it. And we've looked at a couple different types of force, or a couple different units of force. One of those was pounds, and one of those was newtons, which I talked about earlier with the mass times acceleration. There's some conversions between them. The big thing that we need to keep in mind is the consistency in units. So if we're using force in newtons, then the associated length unit that we need to use is meters. Whereas if we're using pounds, we want to use feet as our associated length unit. And that helps to keep everything consistent. Most frequently, we're going to use pounds, force, and feet. And that seems to be pretty common in civil engineering particularly. So for most of this unit, we'll probably use pounds and feet when we're doing our moment and force calculations, as opposed to newtons, whereas pretty much every other area of engineering and science uses the SI system or the newtons. So it's one of those weird quirky things where we tend to use pounds more frequently. You saw that with your modulus of elasticity. We used pounds per square inch. So we're using that pound system when we looked at beam deflection and the modulus of elasticity. So we want to be able to look at the forces acting on an object and combine them together. And we look at it very simply to start out with, and these are going to be the types of problems that you have to do on your assignment for today, is if they're acting in the same direction or they're acting in opposite directions. So if you consider a box which has 5 pounds of force on it acting from the right and maybe 2 pounds of force acting on it from the right, then that's the same as putting a total of 7 pounds of force on it with this blue box. So maybe you and a friend are pushing on a box, and you're much stronger than your friend is, so you're pushing with 5 pounds of force and he's pushing with 2 pounds, and you're pushing in the same direction, but that's the same thing as if you were pushing with a total of 7 pounds of force to the right. Now if we look at this red box, we see 5 pounds going to the right and 2 pounds to the left. So now you and your friend are standing on opposite sides of the box, and you're pushing with 5 pounds of force and they're pushing with 2 pounds of force, well, you're still going to get a net of 3 pounds of force to the right because they're really not pushing with enough force to overcome you. So see how we're just kind of subtracting those values there. Got a couple more examples on this page, and you can go ahead and pause and try this out for yourself. But we'll see with this first box here, I have 3 newtons to the right plus 7 newtons to the right. So that comes out to a total of 7 newtons to the right. In the second one down, I have 3 to the left and 5 to the right. So that's the same as pushing with 2 newtons to the right. 5 newtons minus 3 newtons, right? In the third one, I have 7 newtons to the left and 11 newtons to the right. So that's the same as doing 11 newtons minus 7. And I end up with the same as doing 4 newtons to the right. We can look at slightly more complex ones. So we see in this top one over here that we've got 2 going west and 2 going in the up and down the north and south. So we can combine that north and south. If we have 24 north and 2 south, that's the same as going 22 north. And 16 west plus 36 west is the same thing as going 52 west. And we can put those together to find this resultant. And that's something that we're going to do in the next section or the next part of this class. If you're feeling interested in it, then maybe go ahead and try to figure out what would that be. What would that angle be that I'm acting at? How could I figure out what that R is? Think about your properties of triangles. That may help. And so there's a similar, more complicated example with displacement on the bottom right here.